Thank you, and welcome everybody to today's event, which is the ANSYS Mechanical 18.0 update. We've got a lot of material to cover today, and I'm going to do my best to give you a good idea of what's in 18.0 for mechanical in the time we have allowed. As already announced, if you have questions, please use the Q&A panel within the WebEx meeting center. And the recording, as already stated, will be available in about a week's time. So 18.0 is another really great release for ANSYS Mechanical. We've tried to split down the large number of enhancements and updates into 5 main areas, which I'll go through today. The first is around faster and easier. So this is how we interact with models within mechanical and how we get on with our simulation tasks productively and as easily as possible. Next, moving on, we have material modeling. So looking at some big advancements there into materials. And then following on that, some enhancements around dynamics, both linear and transient dynamics. Then we move on to an exciting topic, additive manufacturing, and then finishing up with a small section on mechanical reliability of electronics. So moving right along now into mechanical ease of use and productivity enhancements. So many of you will be aware that models seldom have just one part, and as soon as you get to models with lots and lots of components in them, then navigating the tree becomes not necessarily difficult, but it's, there's a lot of scrolling involved to get to where you need to do. So over the years, we've introduced a couple of features to make this easier. So we can allowed some feed filtering at the top, also added grouping in previous releases. Now we're allowing sorting, so you can sort your entire tree alphabetically, which is switch on and switch offable. So you can see that on the top right here. And also, if you have multiple environments, such as the example here where we've got static structural, a modal, and a steady state thermal, you can flick out to say which one you want to look at. So if we hit just on modal here, it will hide all of the other simulation environments to make that tree a lot more compact. So just saves a lot of time scrolling up and down to make the model easy to interact with. Also, in terms of the selection information panel, so over on the left here, we can see we've got a couple of areas picked. We've expanded what information is displayed in the information panel at the bottom of the screen to include things like angle between 3 nodes, to include radiuses of curved surfaces or lines, and also areas of faces as well, and node IDs and things like that. So there's a lot more functionality just at your fingertips. You know, clicking on a few entities on the screen will give you some instant feedback in the information panel there at the bottom. We've also expanded on what hotkeys are available. So these are something which are a little bit hidden unless you go and kind of look in the help or pay attention to the menus. Maybe you don't realize all of the hotkeys that are there. So things like Control A, which you're used to in Excel and Word, also usable in mechanical. Added a couple of new ones here. So N for creating name selection, and I for looking at selection information. So if you pick on a vertex or a body, for example, hitting I will give you the selection information panel down in the bottom left under the details pane. As always, the help listing contains all of the details there, so you can kind of more quickly review the hotkeys that are available to you and maybe see some hotkeys that came in previous releases that you didn't know about. In terms of selection as well, so as well as the selection toolbar that was there previously, we've added a selection utilities toolbar now. So this allows you to do things like setting areas of or faces of the same area. So the graphic in the middle there showing the bolt face that we've picked, hitting size and then select all entities of the same size. We'll pick all of the faces of the same size in just a couple of clicks. So again, that makes things a lot more streamlined in terms of interacting with things, and then once you pick those, hitting N for name selection will allow you to create a name selection based on those parts. So a couple of little features there to speed up things. Also, as well as based on sizing, we've also got things based on location, converting between types, so convert to nodes, etc., fixed cylindrical faces, shared topology by material, etc. So quite a few nice features there which allow you to quickly navigate and select around in your model. Another nice new feature in mechanical here is the ability, so you've been able to create path geometry. So this allows you to put a line through a body and plot a result onto it, or a surface. We've now added in a solid. So a solid allows you to create a 3D box under construction geometry. It's just a rectilinear box right now. You can orient it depending on what coordinate system you align it with. But the really kind of neat thing is that you can take this construction geometry and add it to the geometry item. So this becomes part of your assembly. So if you're looking for something where you need a face to push a body up against, or to constrain something, or maybe if you're doing an explicit analysis, you want to look at something like a drop test, then this will allow you to create the body to do that without the need to go back to your CAD system or to SpaceClaim or Design Model or whatever you're using for geometry creation. So that's a really nice feature, and hopefully we can expand on that in future and give more options, but we'll have to see what development come up with. Moving on now to remote points. So previously with remote points we had to have these tied to geometry, so vertexes, faces, bodies, etc. In 18.0 we can now create these as freestanding. So this is essentially a standalone node in space. You can associate an APDL parameter with it. So if you're working with command snippets in mechanical, you've got the option there to grab the ID of the node without having to go in and further modify that. And then you can create things like spring damper systems or connected springs without having to resort to coding these by hand. So it's a really neat feature for a bit more advanced analysis tasks. On the lines of beams and springs and bolts and things, we've added in now a pretension beam connection. So this is really useful. If you've got an assembly with bolted joints and you want to model the pretension of the bolts, you can now do a couple of operations. So you can take out the bolt and replace it with a beam connection. So that was there in previous releases. But the change here at 18.0 is now we can apply a bolt pretension to these beams. So we can load these up as if they were 3D solid geometry. So you save a lot in terms of working out contact between the different pieces. You also save a lot in terms of element count within your model. So it allows you to have the effects of bolt pretensions in your assembly without the overhead of all the actual 3D geometry within there. For those of you working on computers with solid-state disks, they might not be where all your models are saved to. So you might have your projects on a standard platter-based disk, but when you're solving, you want to make use of the solid-state disk. So now you can actually go in and specify the scratch directory. The scratch directory is what the solver uses to write to during the solution process. And if you've got a solid-state disk, that's much faster than a standard disk. So you can specify that scratch directory manually, and then when the solver runs, it will make use of that extra speed boost you've got available to you there. So that's available in tools and options in mechanical. So it could be quite useful for speeding up and making more use of the hardware that you have at your disposal. I touched already on being able to pick up node IDs and edge IDs, so picking interactively on the screen with the mesh selection. You can pick on a node. You can now also select mesh by ID. So if you do right mouse click and select mesh by ID, hotkey M, you can type in the node or element ID and it will highlight on the model where that is. So you can use this in conjunction with obviously the display mesh, but you might also want to use wireframe as well to identify if nodes are in the middle of the model. This could be very useful for maybe under constrained models where you've got parts flying away or contacts not correctly defined. So here you can see you've got an error example where it says internal solution magnitude limit was exceeded. So the problem is the contact's not working, it tells us the node number. We can select mesh by ID, and it'll show us on the screen where that is. So it'll give us a really slick way of diagnosing where the issue in the model is without having to go in and kind of manually figure it out. So it's a really great addition to debugging there. On the post-processing side, a couple of nice additions here. So for thermal analysis, where we've got contact between joints, we're now able to calculate the heat transfer between two parts. So we can drag the contact down to the solution branch, or you can right-click and say create steady-state thermal heat reaction or contact tool from the contact branch itself and get a result there as well. So there's no longer do you have to do this manually with commands. That's available directly in the GUI. It will give you an idea of heat transfer between parts in an assembly, and that's available as a result in watts, as you can see the bottom left here, or whatever units you're working in, and it's parameterized as well. if you're using probes to annotate your model, if you're adding lots of probes to figure out exactly what's going on, where the stress or displacement or whatever result it is you are looking at is clustered on your model, once you add quite a few of these probes, then the screen gets very cluttered. We've now added the ability to move these around interactively, so you can make the screen a bit clearer and easy to understand. And as you're doing these as well, you'll see in the bottom underneath the graphics window where the table is, you have a table of results showing you the result value, the location X, Y, Z, and what it's associated to as well. So it gives you some idea of kind of a summary view of what's going on the screen there. And you can export those to a text file, delete them, do whatever you like with them. Next new addition, I believe this was beta at the previous release, but it's really quite neat. So this is the ability to write out something called an AVZ file or an AVZ file if you're British like I am. This AVZ file can be exported from pretty much anywhere in the tree. We're looking at a thermal result here in the animation. The file can be viewed with a standalone viewer. This is part of the installation at 18 now, and I've put the path down the bottom left of the screen there, so you just need to grab the exe in that part of your installation. So open the AVZ file. You don't need a license, so you can send the AVZ file and viewer to somebody who doesn't have an ANSYS installation, maybe a customer or a client, and they can interact with the file that you sent them. They can look at the plot through the volume. They can hide and suppress individual parts, really investigate what's going on there. They can't change anything. They can just visualize what's going on there. So great tool to add a lot more clarity to what you're looking at or what you're trying to explain to somebody else who doesn't have ANSYS. And that's available to ANSYS Mechanical and every license, and also it's the same functionality that's available in CFD Post as well, so that will work in either environment. Okay, so moving on now to FE import. So this is using external model. So the big changes here really are the amount of information that's imported. So this is bringing in what's sometimes referred to as legacy FE files. So this is CDB files from ANSYS Mechanical APDL, Abacus files or Nastran files, and you might want to do this to continue some work from an old analysis or take work from somebody else who's carried out something in a different package, and you can use this to build an analysis within Mechanical without having to resort to fiddling around with nodes and elements manually. So you can solve and verify these results in Mechanical or indeed in Mechanical APDL. We've added a lot more awareness into here in terms of the amount of data that's brought in. We've also massively sped up the import process and also the geometry synthesis. So we're bringing in nodes and elements with no geometry, and we have to synthesize or make the geometry around those meshes. That's had a big improvement in robustness. So the types of things that are imported now, or additionally imported to where we were previously, so coordinate systems, both elemental and nodal, remote connections, so this is joints between disparate parts of the model. You can fiddle around or change the weighting factors to control the effect of those connections. Constraint equations, so for MEPDL, this is CPs and CEs, Nastran, NPCs, and Abacus equation and NPC tie commands can all be imported. Shell thicknesses for the shell model is imported. You get a table underneath the graphics window when these are imported, and you can highlight all the 3mm or half-inch or 5mm plates that have been imported, and that will show you on the screen interactively which parts are which thickness. And then finally, we also have point masses as well, and this is with node IDs assigned to them as well, so you can identify where point masses have been added to a model. So quite some substantial improvements there in terms of capability for working with external models. So moving on now to HPC, high performance computing. A couple of nice features here. As always, we're constantly looking forward, looking to make everything in Mechanical run faster, as our users are expecting. And for linear dynamics, we actually made quite a big investment in terms of our HPC development here. And the main speed up you'll see is something called frequency domain decomposition. So in the top left here, with the 4 blocks you can see, this is the traditional way of decomposing a model to run on multiple cores. So if you have a 4-core machine, we'll split the FE model up into roughly 4 pieces, or roughly 4 equal pieces, or 4 pieces. And then we'll solve those pieces on the cores, and the information will be passed between those cores as the solution progresses. Frequency domain decomposition basically says we'll take the whole problem and we'll put the whole problem on each of the processors. So if we have 4 processors, we'll put the problem on 1, problem on 2, problem on 3, problem on 4. And each processor will solve a different part of the same problem. So we minimize the amount of information transferred between each processor, but we're solving different frequency aspects. So we've got a couple of examples on the next slide here. So we've got both a cyclic example and a harmonic example. Just to kind of summarize, the speed up is almost linear. It's really, really, really parallelized. So we take a look first at the graph at the top here and look at the purple line. So the purple line is mesh-based decomposition. So we take the mesh and we split it into a number of pieces. And if we look, we see kind of fairly modest speed up as we go from 8 to 16 to 32 to 64 cores with the purple line. The red line is 18.0, so the same methodology as we have right now, and we'll see the speed up is actually much more significant. So as we go from 8 to 16 to 32, if we look at 32, we're over twice as fast as we were at 17.0, and that's just last year. If we switch to the frequency-based, in this case it's cyclic harmonic index decomposition, the speed up is massive. So, you know, it's many, many orders of you know, much, much quicker than using mesh-based decomposition. And for harmonic analysis below, we're just comparing the frequency-based decomposition versus the mesh-based decomposition. Again, both of them scale pretty nicely. So even if you do nothing and you don't adopt this new approach, you're still seeing a nice improvement. If you are able to switch to frequency-based decomposition, though, it's not quite, but it's nearly twice as fast as the improvement we get over the mesh-based. So some very nice speed ups there available to us in 18.0. Now moving on to something called nonlinear adaptivity. So this is where we're looking at models which have very high distortion. So the animation at the top right here is showing a model where we've got the pieces which are contoured, which we have results on. These are hyperelastic materials, and as they deform a lot, the mesh gets distorted to the point where it's no longer valid to continue, so the solver remeshes automatically and continues. This worked pretty nicely at 17. Big change at 18 is it now supports distributed ANSYS, so it's about 3 times faster on 32 cores than it was at 17.0. So it's nothing, you know, no small improvement in terms of speed up. Very nice, and of course there's improvements in robustness as well there as well. We've got a couple more points on LAD further on in the deck as well, which we'll touch on. On fabricated structures, a couple of smaller updates here. First off is around beam modeling. So within SpaceClaim we have beam extraction, so this allows us to take solid models and turn them into beam models. We've got improvements in the way the connections are handled, so detail at the bottom here, automatic creation of connection of beams. And then the really nice piece there is submodeling. So we can go from a beam global model to either a shell or a solid submodel, mapping over the forces and the moments onto the model automatically. And that happens, all the moments and forces are mapped for us. We don't need to do any manual selection there at all. So it's pretty nice and pretty quick way to go from a big global model to a local model with some high fidelity. Also, we've added in a couple of changes in the way we handle intersections. So on the model on the top left here, if we treat the beam in a standard way, so a small beam connected to a large beam, in actual fact what happens on the 3D model is that the beams don't join center to center, they join surface to surface. So the model at the top where it says flexible is actually a little bit too flexible. And the model underneath, the rigid piece, is showing us that the portion of the beam inside the other beam here is treated as rigid, not allowing flexibility. So the actual connection manifests itself as if it were joining at the surface here, which is much more realistic. So the axial offset is detected and helps us improve joint representation. Also got additional capability around end releases. So this is allowing rotation in different directions for jointed connections for these type of beam assemblies. So very useful for offshore analysis. And then finally, just looking at Aqua. So Aqua is our hydrodynamics tool. Big changes here is that we've now pretty much got all of the core solver capabilities into the mechanical environment. So a lot faster for creating models, a lot more convenient. And this is mainly around the workflow angle of things. And as part of this, we've added in meshing physics-based preferences for hydrodynamics. So now we can create meshes specifically for hydrodynamics as a mesh type and then use that within this environment. Also at beta level right now, 18, we're adding the load transfer from hydrodynamic analysis onto a structural analysis. So you can take pressure and wave loadings and put those onto 3D structures. So it's pretty neat there. So a bit more details around meshing now. So quite a few changes in meshing. I'm just going to do a brief highlight today. So first off is the change in terms of how we define the shape checking, if you like. So this is the physics preferences. So now we've moved from having shape checking having been set on every single physics manual into basically saying if you set mechanical, then mechanical will automatically choose the appropriate shape checking options, and you can go in and fiddle around with those if you wish. Added in also an errors and warnings check mesh. So now it will produce a mesh with errors or with warnings, or you can say, no, just go and create me a mesh and I don't really care what's going on there, and then you can investigate manually the quality using the mesh metrics. On the mesh metrics side as well, we've added a new capability. This is to characterize mesh length, which is very useful for explicit analysis, so for looking at the shortest edge length of an element. This will drive your solution time. Also some revised options around Jacobian ratio, so you've got choices there about how the Jacobian ratios are calculated, whether they're calculated when they're wearing mechanical or more in line with how they're wearing mechanical APDL, so you can choose what's going on there. And elements which go into a warning state, you can add to a name selection, and again you can more easily go and investigate where they are. If you want to continue anyway, if you want to change your geometry, you know, you've got the choice about what you want to do there. There's some overall improvements in terms of mesh generated quality. 17.0 was pretty nice, and 18 improved again on this. So top right example here, we see a much more regular mesh on this geometry. We'll also see improvements in mesh patterns on shells. So you'll see the spidering effects around connections are massively reduced. And where the mesher was unable to maintain quads in 17, 18.0 is now much more successful. You'll see around back tip meshing as well, a much more uniform and nicer looking mesh. And I always say that with meshing, if it looks pretty, then you're probably on the right lines. So that's some nice improvements there. Last improvement in meshing is around the local controls of size functions and defeaturing. So similar, well, it's the same example we had before, so we've got lots going on here. We've got a whole pile of bolts, we've got this orangey part with lots of patches on, and then the bulk volume. So the bulk volume is the yellow piece. We can just get away with our normal meshing. We might want to do some mesh-based defeaturing, so that the blue panel here we've put as a virtual cell, and we've meshed right over that. We've done some proximity size-based function at the top here. We want to capture all the detail, and we've got uniform size function on the bolts here. So we've got different size functions for different parts of the assembly, which kind of allows us a lot more control than we had affordable to us before. So moving on now to SpaceClaim, a couple of nice highlights here. First off, in the top right here, there's been a change to the way that the suppress and hide function works. So mechanical, if we hide something, it's still active, it still works in the model. If we suppress something, then it's not active in the physics and it doesn't solve. The same logic now applies in SpaceClaim as well. So if you hide something, it will still come through to mechanical. If you right-click and say exclude from physics, you get a little no entry sign over the geometry, and that will not come through to mechanical. So the behavior is much more consistent with the rest of the workbench kind of environment of products. We've expanded and updated our scripting capability in SpaceClaim, so now things like body IDs are maintained so that the persistency of the scripts you might write are more reliable, and also created things like equation-driven geometry, so we can define surfaces, helixes, shapes using formula as well. So we've got, we can fiddle around with those until we get exactly what we want, and then use that to build our geometry or slicing planes for modeling further down. Also in SpaceClaim has been the expansion of the skin and shrink wrap. So this is generally for dealing with STL type files, so much more control around creating patches, control of sample points for these patches, and then producing a usable geometry from an STL file as an import. We'll touch on this again a little bit later when we move on to talking about the additive manufacturing and topology optimization. But this is part and parcel of the whole process, so we can take a faceted initial model, few options here in SpaceClaim, so select the areas we want to retain, do some smoothing, and then get something which looks pretty nice, and then go ahead and carry out our validation step. So some nice changes there in SpaceClaim. So moving on now to contact, always a good topic for discussion. This is around contact searching, and this isn't contact detection. This is something that happens within the solver during an analysis. So as the solution progresses, the solver needs to look and figure out where the contact is in the model and what's touching what. And this searching process has been speeded up by, you can see in the bottom table here, so if you look at the number at the bottom right, the actual searching part has been speeding up by a factor of 17 on this particular example. And it's not a big example. And this results in an overall solution time improvement of twice as fast. So even on a small and relatively simple model like this, by changing the way something happens within the solver and how it deals with contact, this makes a big difference here. And also in terms of general contact, which is something available in mechanical APDL and I think Workbench with some commands, this will have a big impact here when you have a large number of target elements. Also on contact we changed the algorithm, so this is projection-based detection for MPC contact. So for MPC, there's two ways of calculating the contact detection. One is projection-based. It's much more accurate, but it's slower. And the other one is nodal detection, which is faster. So if we compare say 18 nodal detection with 17 MPC detection, you'll see that it's about 8 times faster to use nodal detection than it is MPC. Again, this is fine, and it will give you a quicker solution, but it won't give you the accuracy. So the changes in 18 around projection-based contact detection and the speed afforded to us by that gets us pretty close to nodal detection in terms of time. So we're speeding up over 7 times where we were in 17. And this gives us nearly the same speed as we'd get with nodal detection, but allows us the higher fidelity of projection-based contact. So great for things like gasket analysis, where we need to know exactly what's going on in the interface. Good for analysis with fracture meshes in, and also things like acoustic FSI modal analysis as well. So lots of applications there, and a big impact for hopefully many users. Also on contact for multi-physics, so this is the ability to support the diffusion degree of freedom. So this is the flow of material or electrons through electric current across a model. And we're actually looking at dissimilar meshes, so we're using contact between the parts here. And now we can allow this degree of freedom to be transferred throughout the contact. So for those of you interested in this, it could be quite a big benefit. It allows us to have moving parts, allows us to have dissimilar meshes between pieces where we need to capture this type of behavior. And then finally, another enhancement around general contact. So some small, well, not small, but some fairly significant performance improvements. Additional support for vertex to surface contact. Also bigger accuracy on things like beam cross-section contact, so we're actually basing it on the beam cross-section rather than just the center line of the beam. And then on things like fluid pressure penetration, so the penetration path is recomputed, if you wish, based on the status during the solution. So if you're assembling things, you can model this more accurately using this approach. Okay, so moving on to what seems to be a very hot topic right now is materials. and I keep telling people this, but this was my least favourite topic at university, but it seems becoming more and more important. So I'm glad to see that we're making some good steps forward here on materials. The first on this is is talking about thermomechanical fatigue. Sorry. And basically what we're looking at here is a material model which will capture the ratcheting and the static recovery of the back stress within the material. So this allows things like low cycle fatigue behavior to be much more accurately captured for things like turbine blades, jet engines, things like that. This behavior is particularly interesting and particularly important to capture. So it's a good addition to our material models there and very useful indeed. And then on the field-dependent material, so there was some previous exposure to this. This has been further expanded. So predefined material list has been grown to include things like time, pore pressure, spatial location, displacement, thermal expansion density. So the solver uses some interpolation between these data points to figure out exactly what's going on at specific elements and particular points within an element to get the material property values. And we can model things now based on these values, things like powder compaction. So we have an example here showing different loads and different densities of material based on their location. So we're looking at Young's modulus based on different thermal coefficients. So we've got numerous things going on in this model here, afforded to us by this field-dependent material property. Another cool thing is the ability to now use these field material, variable material fields within mechanical. So we have a model here where we're using external data, which contains our topological densities. We have these to model, and they appear as an item under the geometry, and then you can map these to say, okay, this is my plotted material density based on my input. So if you're doing things like bone scans, or maybe you're doing something where materials semi-porous or various steps, like a soil or something, then importing the material properties via external data now allows you to model this within mechanical. So that's a lot more straightforward than trying to have to wrestle with text files and do some manual mapping yourself. You can do this interactively within mechanical and visualize it as well to check it's correct. So I think that's really neat. On geomechanics, so modeling of soils, concretes, that kind of thing for offshore, civil, mining, and construction applications. We've further expanded our material library to include something called the Menetray-Willen material model. So this is very good at modeling concrete. So the other material models we have are fairly widely used. Menetray-Willen ones, triple saying that, Menetray-Willen material has the compressive yield surface is well captured, but also the tensile yield surface, something which maybe wasn't captured in quite as good detail with previous material models, is much more accurately represented using this approach. So you don't need to use any parameter fitting with this one, and it includes models for compression, hardening, softening, and tension softening as well, which is probably not as well captured with the material models previously. Also, we've expanded our capability on structural-pore-fluid models. So this is porous structures such as soils or sands, and we've now got the ability to have a mixture of materials. So we have the solid air or voids, and then also water, so that we can have partly saturated soils modeled more accurately. So we can now do also fully coupled poro-thermomechanical, which allows us to model the heat transfer in some structures like this. So again, very, very important for offshore applications or civil applications where you're dealing with geomechanical materials which rely heavily on a good understanding of the material below what you're building or around what you're building. And then finally, materials we'll touch on, again, one more time on nonlinear adaptivity. So there's improvements here, so around the way the retaining of the mesh is handled. So basically what happened before was we'd remesh a lot during the solution. So bed splay animation at the top here on 17. you'll see the model remeshes completely as we go through the solution. So the solution time for that model, which is pretty impressive in its own right, is 300 seconds, or just over 300 seconds. And 18.0, by minimizing the remeshing process, we can cut this down in terms of number of iterations, and also as a consequence, the solution time drops from 317 to less than 190 seconds. So quite nice improvements there. And also at 18.0, we've added the support for 2D thermal structural coupled physics. So this is some thermal forming of an I-beam you can see going on underneath here. So we're coupling the structural and the thermal behavior of the material in 2D. So a pretty complex problem being solved there within mechanical using this technology. So it's quite nice. Okay, so I want to move on to something called based around or themed around tire simulation. It's not solved. This technology isn't solely aimed at tire simulation, but tire simulation shows us some fairly unique challenges. The tires in your vehicle are pretty complex in terms of what they're made up of. You've got some beads around where the tire is held onto the rim. You've got various belts going around the circumference of the wheel. You've got the treads. You've got some reinforcements, some sidewall reinforcements, and lots of stuff going on in there. It's a very complex product. And the types of challenges you might be interested in solving if you're a tire manufacturer, or indeed involved in something where you've got reinforcements or 2D like structures, would be things like putting the tires on the rims, the inflation, looking at the footprint, and then moving on all the way to hydroplaning. So let's talk a little bit about some of those applications or some of those challenges. So first of all is the modeling of the reinforcements. So this is ReBars. So similar to what you might find in concrete, and indeed they could be used in concrete, so modeling the steel reinforcements within the solid model. We can now model this in an almost completely automated way. So we have the line bodies representing where the reinforcements are, we have the solid mesh to model where the tire is, and we can automatically map the reinforcements into the solid geometry, solid elements, if you like, sorry, not geometry. And these are embedded as a reinforcement. They can have different shapes, material properties, orientations, etc. This happens automatically. We can change the mesh of the tire without having to remesh or reconfigure all the reinforcements. So it's a really, really quick way, a really, really accurate way of modeling these reinforcements in the geometry. So look at the example here where we've got an uneven parent geometry with lots of reinforcements going through it. And where the reinforcements don't go all the way through the element, so we have where the purple is within the volume, the blue line here is showing where the reinforcement doesn't go in the element, and then the reinforcement here goes back inside. Those reinforcements are mapped into this volume element, and then the solid mesh automatically for us, and then this piece will go into the neighbouring element. So it allows us to do 3D discrete reinforcements very, very rapidly in pretty much any shape of mesh we like, so that can be distorted or not. Additionally to that, so again, keeping with the same topic as tires, is the ability to do 2D axisymmetric elements, or 2D axisymmetric models, and then apply torsion to them. So this basically is allowing us to do a 2D analysis and then put a load into the plane effectively. So we're seeing here, we're putting a torsion load on this model around here, and we're seeing the resultant stress S, X, Z. This is into the page around the axis of where the tire is, and then from that we can go and look at other analysis results. So another example of where that might be useful is in looking at a 2D axisymmetric cylinder where we're applying some twist load to it. So the 2D axisymmetric is on the top here. Our axis is somewhere over here, fixing the top, applying some load at the bottom, sorry. And then we can do some expansion of the result to plot the twist of the model in 3D. And this solution time takes us, I believe this is in seconds, so not very long at all. And if we compare this to a 3D model, the same thing, so not overly refined, so still fairly light mesh. This takes us 68, well, nearly 69 seconds, so much longer for a 3D analysis compared to 2D analysis. And we can see that, where this is appropriate, this could be a big time saver indeed to allow us to go from 2D, carry out 2D analysis rather than a 3D one with a bigger computational overhead. Once you've carried out the 2D analysis and you're happy with what you want to do, you might want to take that to a 3D analysis now you can continue your 2D analysis onto a 3D analysis. So what happens here is we're going to take the mapping of the current stress state, the deformations, and also the contacts, and create a 3D model automatically for you from this. So this is really, really powerful stuff. For the right type of analysis, this could allow you to carry out lots of studies in 2D. Once you feel you're near a solution and want to carry on and do a 3D analysis, maybe you've got some non-2D axisymmetric loads you want to apply, you could do this analysis, continue from 2D to 3D, and then continue the solution process. So this could be a boon for people working with this type of geometry. Another example here is something like a tire analysis, so again, going from a 2D to 3D process. So moving on now to, excuse me, to fracture mechanics. So I've had a few questions on this actually. So we've shown fracture mechanics before, and people have picked up that we're using tetrahedral elements around the crack tip. We actually have some proprietary technology called unstructured mesh method. So this uses tech meshing at the cracks, a much quicker workflow, so you don't need to go and dissect your model, specify sweep directions and element sizes and things around the crack tip. You can use a tech mesh to generate this, so the workflow is much faster. And you can see the accuracy on the graph there maps very, very well with the actual results from test. And then the additional results here are the addition of initial strains and calculation of J interval stress intensity factors when we're looking at body forces. So, for example, gravity loading here. So that's a really nice improvement there. For fracture analysis, it means you can carry out lots of studies without having to, as I say, spend a lot of time preparing your model and meshing in the correct way to carry out analysis. Okay, so on to composites analysis now. So some changes here around the way we model thickness of material. So two scenarios, ply tapering and using a cutoff rule. So cutoff rule probably defined by some, or allows us to model layers of material which don't go all the way to the end of the part. So maybe we've got 4 in the middle and 2 at the end. And we can choose which way we model the thickness or calculate the thickness. We can either use element-based thickness or node-based thickness. And these are new for us at 18. You can see the effect of creating a more realistic, less wobbly looking 3D solid mesh based on which method you choose there. So it allows us to find this varying thicknesses of nodes instead of elements and gives us improved solid model extrusion to get much more accuracy. And we've also added support for the field variable material properties for this as well. Probably more useful, bigger impact in terms of usability is we've now added the failure post-processing directly within ANSYS Mechanical. So you can use ACP pre to define your layups, calculate draping, specify where the different materials are applied on your model, take this into Mechanical, carry out your simulation, then you can actually do your composite failure plot within Mechanical as well. So your workflow is much more condensed, using less interface there, and you can get through your analysis process much quicker. Also available on Linux as well as Windows as well, so that's quite a nice addition. There's numerous other enhancements here in Mechanical as well, so better representation of butt joints, which hold more accurately the thicknesses, better CAD geometry handling, which improves the workflow as well, and also numerous other enhancements as well. So ACP has ANSYS Composites has seen a nice boost at 18 as well. So on the topic of dynamics now, quite a few updates here to talk about. So first of all is the effect of, so for turbo machinery, we calculate in CFD the stresses, or sorry, not stresses, the pressures on our turbine blades here. So we use a CFD solver to calculate that pretty accurately. And as one of the outputs from that, we can actually get some impact on the damping. So if we want to go and carry out a harmonic analysis from that, we can take the damping from the CFD analysis and use this to carry out the harmonic force response analysis on the structure. So we get a much more accurate representation of what the fluids are doing to the structure in terms of its vibrational response. So adding a lot more fidelity there, and it's an easy way to do this using new AeroCoif command. On the topic of bearings, so this is a bearing sleeve we're looking at here. We've a new element added. So this is a new 3D element, fluid 218. And this allows us to model the fluid between rotating structures. So if we look at a bearing supported by a fluid, and between the two surfaces, we can model the fluid flow between these two pieces to give us a better representation of what's going on there. So this makes a big impact on things like rotational damping. So what happens when we're spinning it up, what does the bearing do to our dynamic response? And this allows us to actually carry on and take it all the way through to a rotordynamics analysis as well. So component node synthesis. So this is the ability to take a full 3D solid meshed part and condense it down to a super element, and then carry out a dynamic analysis. So the back loader here solves almost as quick as if it's a completely rigid model. We sped up the process of going from the super element to the full 3D model for results processing. This is called an expansion pass. So we've speeded that up quite a lot, and also reduced the hit on disk space when you choose not to save the factorized matrix. So these are both applicable within the flexible rigid dynamics calculation as shown. So we can see that most of the model there is rigid with no contours on it, and just two of the parts have flexibility, and we're looking at the stress results, which have been expanded from the CMS components. For harmonic and random vibration, we've expanded the scope of the fatigue tool. So the fatigue tool allows us to look at things like life and damage that parts or assemblies see during their lifetime. So basically we go in and say we want to use these different PSD or harmonic excitations, and say how long the part is exposed to this environment, and the fatigue tool will allow us to predict the life or the damage exposed by these parts. So it's a nice expansion there to what we were able to do with the fatigue tool before, where we were doing stress, thermal stressing and stress results and taking those and doing a fatigue analysis. We can now do this within linear dynamics as well. In terms of rigid body dynamics, a couple of nice new features, well, quite a few new features here. First, the joint friction, so we can now specify some friction coefficient around a specific joint. We can export deformed geometry from an RDB simulation, so if we move a joint so many angles, so many degrees, we can export that geometry and use it downstream. We can apply damping. And probably the nice thing, or one of the things that I got overly excited about for no good reason, was the plotting of the motion of parts. So we can do a trace plot to show where a part has been in space. So if we're looking to see how far did a part deform and is it going to intersect with somewhere where another piece has been, we can use the trace plot functionality to capture that. So it's quite nice. And also we've changed the biggest feature I missed to point out is the fact that the time stepping scheme here, so if something goes on in the solver, means that big speed of models with contact. So this is a model of the gear train, which many of you have seen before, 18.0, much faster than it was at 17 due to this change in time stepping scheme. In terms of explicit dynamics as well, in Mechanical Enterprise, for those who have access to that, we've now exposed the multi-material Euler capabilities, and this allows us to model both the structural response and the fluid. So this is a fluid-filled vessel being dropped, and the multi-material Euler solver allows us to capture both of those for fluid structure interaction models, so looking at things like sloshing and what happens to the fluid within the volume as it can slosh and maybe load the part in a different way. As well as some other improvements around bonding contact, remote forces, and being able to post while solve, which is pretty exciting stuff. Okay, so moving on now to topology optimization, probably one of the things that we've had the most questions about on 18.0. So in terms of how it's delivered to our customers, all users with our current product lineup, so that's Design Space, Mechanical Pro, Mechanical Premium, Mechanical Enterprise, get topology optimization 18.0. So topology optimization is part of an exercise in realizing, making the best use of the technologies which are coming about around additive manufacture. So topology optimization allows us to take a volume of material, apply some loads to it, and ask the solver to figure out where the material should be. So it's a physics-based solver. So we can specify things, the things that we want to optimize on. So we can specify stiffness, we can specify which loads we want, we can specify, if we're doing a modal analysis, what frequencies we want to get to, whether we want to maximize those, or whether we want to minimize mass or volume of a part. So you set up the analysis you would do normally, a static structural we see here, and then once that's been carried out, you link it to the new analysis system, topology optimization, and then carry out your solution. As I say, it's native to mechanical, so it's part of the analysis tree here, and you can insert the different constraints, so you can have things like minimum member size, pull-out direction, which is beta right now. You can specify the response constraints, so whether you want to look at the stresses, displacements, volumes and masses, etc., to carry out your solution. Once you've carried out that, you will get an output geometry, which will look faceted like this. You can link that system directly to something called a validation system. So right-clicking on the results here allows you to link to a validation system. We'll take all your boundary conditions through an initial static structural analysis, create and add those in automatically. You just need a couple of clicks to finish setting that up. Then you can carry out a validation. You can use SpaceClaim to say, I want to keep certain faces to be flat. I want to make sure I have a round face on here. I want to make sure I've got room for a bolt over here. And then once that's ready to go, you can carry out a validation analysis. The design validation workflow is actually absolutely critical. You want to make sure that the optimized topology you're creating is valid and is accurately representing what you want to achieve. So if you want it to maintain a load in three directions, you want to be able to validate that happens with this optimized topology. So this process allows you to check that happens, and then you can prepare that for printing afterwards, sending it to a 3D printer for manufacture. So moving on now to reliability of electronics. So we've expanded on what was available in 17 here. Main changes here are around, first of all, accurately modeling vias. So now we're able to look at variable and the hollow vias rather than just solid, which we had at 17. We now got additional options around dual heat exporting from SI Wave, which is a signal integrity solver that we have, and also additional capabilities in terms of what type of files we can read in from ECAD. So this is the geometry, the file that circuit board designers use to lay out PCBs. So we've got three examples here to show, one model with three different methodologies. The first one is a thermal model, which is layer-based. So we're using mapping to import the heat load from SI Wave. The second model is a layer-based model, so it's actually no mapping. We're doing element-based loading here, so very high fidelity, so quite a big model. And the last one here is thermal layer topology. So basically, we've just got the layers of the model, no geometry imports there whatsoever, and we're using the trace mapping capability within mechanical. The results and comparison between the three are that the results are very, very close indeed, so less than 1% variance between them. So the trace mapping approach shows really good agreement between the high fidelity models, but takes a fraction of the time to set up and solve. So if you want to actually get some solutions and try some different design iterations, cooling regimes, etc., this approach will allow you to carry out that in many times faster than you would be able to do if you're doing full fidelity 3D models with all the trace maps individually. On the topic of MEMS as well, we've expanded what we can do here with the 22X elements. So these MEMS are micro-electrical mechanical systems. So used in your phone for things like the gyro sensor, which way up it is, using cameras for focusing, that kind of stuff. 22X elements have got a lot of coupling in them, so we can couple different physics fields. And at 18 now we've added in the capability to do something called linear perturbation. So this allows us to effectively pre-stress these elements with some load and then apply some excitation on them. So this is actually much closer to what happens in reality. So generally we'll put some biasing on with some voltage, and then we'll look at the response to some input excitation. so the linear perturbation is critical to accuracy in that area there. Okay, so that's been an absolute fly-through of what we have available to us in 18.0. There'll be more webinar updates throughout the year, and we encourage you to reach out to your local support teams if you've got topics of particular interest. There's an awful lot to cover, and apologies for not being able to go into more depth with time around, but I'm hoping you found today useful. Just to finish off, I wanted to recap some of the additional functionality in 18.0. First of which is the topology optimization, which we talked about towards the end there, is in all current mechanical products. Also the addition of Design Explorer, and I'll show you exactly what the product mapping looks like in a second. There's a little bit of a change to HPC packs. So now rather than 8 cores, a HPC pack will give you access to 10 cores. And also by default, we now enable 2 cores for both Aqua, the RBD solver, rigid body dynamics, and explicit dynamics within mechanical. So just to give you a look at the packaging, you'll see the changes highlighted there in yellow. So optimization really now available in every flavor for every user of ANSYS Mechanical at 18.0. So I'm hoping that a lot of people take advantage of that, and instead of just producing a design that meets their criteria, they really go out and look for the best design they possibly can. And I believe that with the offering we have right now, that'll allow a lot of innovation from our customers. Just on a note, there's some other changes as a final note. So as I said, the HPC chip packs will change at 18.0 a little bit. This affects both the new CFD products as well as the mechanical products. The first HPC pack will now enable 10 cores. The second pack, so if you're using 2 packs with the solver, that stays at 32 though. And at 18.0, if you're aware that the CFD product changes, so some product changes around the CFD products at 18.0, these will not change those of you with the multi-physics bundle products. So if you've got mechanical CFD or mechanical CFD Maxwell, the CFD products you get with those licenses at 18.0 at least is going to stay as it is right now. Okay, so just to summarize then, first of all, when you install 18.0, the first thing you see when you open up the package will be a mechanical highlights page. This is going to give you a flavor of some of the major enhancement themes. So you'll be able to click on the links here and it'll spin down to the relevant point of the page. This just shows it the first time you open mechanical. If you want to get back to it, hit on project and then on worksheet, allow you to look at the topics maybe you've forgotten, something we were talking about today and you wanted to refer back to it. And as always, the release notes that we ship with every version of our software, both as part of the installation and on the support.ansys.com, will contain a lot more detail than we're probably covering